Okay, welcome to a pre-calculus video. This is a video over section 8, which is called Piecewise Defined Functions. What we want to do today is we want to be able to graph piecewise defined functions. We want to evaluate piecewise defined functions, and we want to determine the domain and range and continuity of a piecewise defined function. So before we do anything, let's kind of talk about what a piecewise defined function is. A piecewise means, and it's kind of I always struggled with piecewise defined functions. Eventually it became very clear to me. But the reason why they call them piecewise is because they are pieces of different graphs all on one graph. Okay? And so that, to me, that's what makes sense to me, is that you've got these different pieces of graphs over different intervals. Okay? So let's just kind of take a look. We had talked the other day about the function f of x is equal to the absolute value of x, right? Yeah. And you see that graph down here, okay? However, what we need to do is we can define this function as two different functions. Okay? So here's what you have. When x is greater than 0, greater than or equal to 0, then, so over that interval, you have the graph of just x with a slope of 1, y-intercept of 0. And that's this graph right here in red. Okay? But then, when x is less than 0, okay, when x is negative, you have the graph of negative x, where you have a slope of negative 1, y-intercept of 0. And so you get this. And that's the idea, is that I have two different graphs. One's in blue, one's in red. But they are defined over a specific interval. And so we have to understand what this inequality notation means and where these functions exist. Okay? So this part right here, when you have a piecewise defined function, this is the function itself. Okay? These are the functions. And this part right here is where they exist. Okay? And that's the idea. All right? So let's go ahead, let's take a look at another one. Okay, a piecewise defined function here. And so a piecewise function, piecewise defined function is a function that applies different rules for different domain values. Okay? In layman's terms, graph it where it exists. Okay? So let's take a look at this first one here. I have the equation negative x minus 3, okay? And that function exists between negative 5 and negative 1. So there's a couple of ways to go about this, all right? But I'm going to do negative x minus 3. And I'm just going to kind of graph that function here and just kind of plot some points. I know that this function has a y-intercept. A y-intercept of negative 3. Okay? And then we have a slope of negative 1. So I'm just going to kind of make a graph here that has a slope of negative 1. And the thing about it is I know that this graph is only defined between negative 5 and negative 1. So I don't really even need this value here. But what I've got, so if I were to draw this graph, I would draw it right here. Oops, let me color it in. So from negative 5 all the way down to negative 1. That's where that graph exists, okay? Disregard this point right here. I just did that so I can graph it. And then we have this other graph of x minus 1, and that is defined between negative 1 and positive 4, okay? So if I come over here and I say, all right, x minus 1, that's a y-intercept of negative 1. So y-intercept there. and then a slope of positive 1. And we're only going up to 4, so let me do this, just kind of plot these points here, and then all the way down here. So from negative 1 to positive 4, and that's my graph. Okay, so you're just, you know how to graph these linear functions. You just only graph them over the intervals that they're at. So what?
So it's like limits?
Yeah, they're like bounded. Yeah. So hopefully that makes sense. Okay, in layman's terms. It's kind of hard to do. It's kind of hard to see. And we'll kind of go through these on some Desmos things and all that. All right, so then it says, okay, let g be the piecewise defined function below. G of x is equal to this x plus 4, and that's defined between negative 5 and negative 1, and then 2 minus x between 1 and 5. Okay, so real quick, I want you guys to draw a graph real quick. Okay, and we'll go ahead and we'll number this from negative 1 to negative 5. 1, 2, 3, 4, 5. And then x plus 4. Okay, 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Okay. Now, what I want you guys to do, and just kind of, all I want you to do is to try this on your own and try and graph this on your own. Okay. Let me give you a minute to do that. Okay, so we got this graphed. We took a little bit of time to do that. And then what we're being asked to do is we want to evaluate the function at these different values. This is where things kind of get tricky. So if it wants me to evaluate g of negative 4, okay, negative 4 is right here. It's going to go on the red graph because negative 4 is in between negative 5 and negative 1. So when you're evaluating these functions, you have to look at the domain of each of these. Where do they exist? Negative 4 is in between negative 5 and negative 1, so I'm going to plug it into here. So this would give me negative 4 plus 4, which gives me a value of 0. And you can also see that that point is right here on that graph, negative 4, 0. Okay? Let's plug in negative 2. Okay, again, negative 2 is in between negative 5 and negative 1. It's right here. Okay, I think it'll be a value of actually 2. But we're going to plug in negative 2 into this function here. All right? So you get negative 2 plus 4, which gives you a value of positive 2. Okay? Now, if I plug in 0, okay, 0, that domain is in between negative 1 and 5. So I have to use the bottom function when I'm plugging in 0. See how 0 is right here and it's on the blue function? So therefore, I have to plug in 0, and I just get 2 minus 0, which gives me a value of 2.
So g of negative 2 and g of 0 are both 2 then?
They are, but you get them using different functions. I mean, the thing about it is that, here's that point here on that one. Here's the point on the other one. Okay? So, here's 0. 0 is in this interval between negative 1 and 5.
Yeah.
So I have to plug it into this function.
Okay.
Does that make sense?
Yeah.
Yeah. Good. Okay. G of 3, okay, G of 3 is a positive 3. It's in between negative 1 and 5, so I'm going to use this function. So then I'm going to do 2 minus 3, which gives me a value of negative 1. Okay, and you can see that point over here. All right. G of 4, again, is in this interval from negative 1 to 5. So I do 2 minus 4 to give me negative 2. Okay? Yeah, and the thing of it is, it's really not that bad if you understand it.
Yeah.
You just got to understand it. If you know what you're doing, then it's really easy. You just got to get used to it. Okay? Okay. On this one, it actually tells us, okay, which of these is the graph, and we've already done that up here. So the graph is this one right here, right? Yeah. Easy peasy. Okay, on this one, you have these different graphs. Okay, you have this one function here. And what it wants us to do is to figure out the domain of each piece and then the rule for each piece. Okay, rule, that's another way of me saying the word equation. Okay, an equation or function. Okay, so, all right, so let's just take a look here. Let's take a look at part 1 for piece number 1. Okay, and that piece, what's the domain? That domain exists between -4 and -1. And so let me do this. I'm going to do -4 is less than or equal to x is less than -1. Okay? And then the domain for piece number 2, okay, just goes from -1 to +1. Okay, and I'm going to do -1 is less than or equal to x is less than 1. And then the domain for part 3 goes from 1 to 5. Okay? And notice how I'm just choosing x values. I'm figuring out where does this function exist on, what x values does these pieces exist. So I'm going to say that 1 is less than or equal to x is less than or equal to 5. Okay? Now the thing about it is, because these graphs connect at these 2 points here, notice how I didn't include -1 on this first part, okay? And how I didn't include 1 on this on piece 2, but I include them, so when I didn't include -1 on this first part, I included it on the second part. We'll kind of talk about what that means.
Oh, because it's in both lines?
Yeah, because I don't want to define it for both. I'm going to define it for one of them, okay? And there's a couple different ways you could probably write this to make sense of it because they connect, but sometimes there are pieces that we'll have to really take a look at. Okay, on this one, now we need to come up with the equations for piece 1, piece 2, and piece 3. The easiest one that we can come up with is piece 2. It's a horizontal line. Do you guys know what function that is? Here.
It's just 0.
It's not 0.
The slope is 0.
The slope is 0, so it's a horizontal line, so it's going to be a constant. You guys know what that function is? It's not just x. That means it would have a slope. The rule for piece 2 is just 1. If you have the line y equals 1, then that's a function that goes through 1 on the graph. It's a horizontal line. Okay? Okay, a rule for piece 1. Now, piece 1, what's the slope of piece 1? -1. So I'm going to do -x. And then if this were to continue, the y-intercept would be 0. So the rule for piece 1 is just -x. Okay? Now the rule for piece 2, or I'm sorry, piece 3, this one has a slope of -1. But if you were to continue this graph through, it would have a y-intercept of +2. So I'm going to write this as -x plus 2. Okay? All right, now we don't always have to have linear functions, straight lines that are piecewise functions, okay? You can have, in this example here, okay, when x is less than 0, so when x is negative on this side of the graph, we just have the line just y equals x, this graph right here. Then all of a sudden, at 0, it changes, and it becomes x squared. And so anything that's larger than 0, when x is positive, is just x squared. And you have a parabola. Okay? Same thing on this next one, function g. Okay? When x is less than or equal to 0, when x is negative, on this side of the graph, you have a parabola, x squared. Okay? Then at 0, that function changes, and then you have the square root of x, the eyebrow. Okay? The next one, okay, when x is less than or equal to 0, when x is negative, you actually have a cubic function, x cubed plus 1. All right, and then you hit at 0, and then the function changes to 2 to the negative x power, and it changes to an exponential function. Okay? So you can have two different graphs on the same function if you define them. Okay? Pretty good stuff. Okay. All right, on this one, it says complete the definition of the piecewise defined function by identifying the domain of each piece. So here, okay, on this graph, you have the line y equals negative x. So you have a line, slope of negative 1, goes through the y-intercept of 0. And we want to figure out, where does that exist? X is less than what? So this value here, where this line stops and it changes, has the x value of positive 1. So A is equal to positive 1. Okay? And then the function negative 1, where you have a horizontal line through negative 1, exists between 1 and positive 3. So B is equal to 3. Okay? And then beyond 3, you have a quadratic. You have the point x minus 3 quantity squared minus 1, and that graph goes up like this. Okay? Yeah, exactly. Okay, so now we go, okay, well, what's the range of this function? Okay, we know the domain, but what's the range? And the range is, the y values. Where do we start and where do we go up from there? And we start at negative 1, okay? We don't have any y values that are below negative 1. But we have to include negative 1 because we have actual y values at negative 1. So therefore, we choose this one because the bracket means that we include negative 1. Okay? All right, and then it says, which rules define the function whose graph is shown? So here's what I've got. When x is less than negative 2, so here's negative 2. When x is to the left of that, when it's less than that, I want to write down the function for this. And the function that's less than negative 2, this function here is a horizontal line, and that value is a value of negative 4. So negative 4, okay? In between negative 2 and 0, okay, in between negative 2 and 0, we have this graph here, which is a parabola that opens down and goes through the origin, all right? And that would be the parabola negative x squared. Okay? And then between 0 and 2, you have a parabola that opens up, and so we would just call that positive x squared. All right? And then when x is larger than 2, okay, we have a horizontal line, and that has a value of just positive 4. Okay? Reasonable? Okay. Okay, the next thing we need to talk about is a continuous function. We've kind of talked about this a little bit, but it really means a lot when we start talking about piecewise functions. A continuous function, and this is pretty good. It says, is a function whose graph has no holes, jumps, or breaks. Basically, and I think we've written this down before, a continuous function is a function, so where you draw a function without lifting the pencil. Remember this? Okay. So therefore, all right, this is a continuous function here because I can draw this graph, and the graph does change. I've got this line here and it changes to a horizontal line, and then we get this positive slope here. Okay, but it's continuous because I can draw this without picking up my pencil. Okay, on the next one, the reason that it's not continuous is because when I draw this, I have this line, negative slope, goes way down negative. All of a sudden, I have to lift up my pencil again to start drawing up here, and then it goes back up. All right, so it's kind of tricky, all right, but it's just, if you have any holes, and this was a hole here, hole, it's a kind of a hole and a jump and or a break in a graph, okay? So we have this thing called jump discontinuity, all right? And there's that function here, negative 0.25 x plus 1.25 is here, okay? And then this is the graph negative 2x plus 3. And then this is the graph x minus 2, okay? But the thing of it is that these two graphs don't connect, okay? And if you look at this, and if you plugged in, say, 3 into this part, and you said negative 2 times 3 plus 3, then that's going to give you, what is that, negative 6 plus 3, which gives you negative 3, okay? And that's that y value down here, okay? That's how you get that point down there. But if I plug in 3 into this function, and I do 3 minus 2, that's just going to give me 1, okay? And that's where I get this function here. That's where I get that point there. And so these are different, okay? These are not the same. These are not the same. And that's when you know that you have a jump discontinuity. Is if you plug in that point and you get two different y values out of it, like you did here.
Oh, yeah.
Because I'm plugging in 3, but when I plug in 3 into this part, I get 1. When I plug in 3 into this part, I get negative 3.
Yeah.
I get two different y values.
So it's not a function as well?
Well, it's still a function. It's just not continuous.
Okay.
It has a jump. It's it's discontinuous, not continuous. Yeah, it's still a function.
Oh yeah, you're doing like ones where you're just like waving like back and forth.
Mm-hmm. Well, and the other thing you have to realize is that this, I'm just plugging in 3 into both of these so you can kind of see it. But 3 is defined for this middle section here, for negative 2x plus 3. Okay, we include 3 on that. We don't include 3 on the other one. That's why there's a hole on that graph at that point. Okay? All right. It says use this graph to answer the questions below. Okay. Let's take a look at this one. This one's really important. Okay, it says what is the value of f of negative 3? So I'm going to plug in negative 3 into this graph. And what's my corresponding y value? When x is negative 3, what's my y value on that one?
Or would it only be 1 since the other one's saying, since the open circle is saying that it's not equal to that point?
Right. The open circle means that we don't include negative 3 on this portion of the graph. We have to include it on this portion of the graph.
Okay.
So the y value, and that's the thing, you have to look, okay, where do I have a point? If I plug in negative 3, okay, I'm going up 1, 2, 3. There's no point here. There's a hole. That's my value here, which is a value of 4. So f of negative 3 is equal to positive 4. Okay? And the other thing to do is if you look at your equation here, okay, it says x is less than or equal to negative 3 on your domain. So you would want to use this function here, x plus 7. And if you said, okay, well, if I'm going to find f of negative 3, well, then I'm plugging it into this portion here, and that's going to give me negative 3 plus 7, which gives us gives us positive 4. Okay? All right, and then it says, what's the range of this graph? Or what's the domain of this graph, and what is the range? Now, the domain, okay, we have values from negative infinity all the way up to negative 3. Okay, we jump down, okay, and we still, we include negative 3, but then the graph picks up here and goes all the way to 0, changes to the square root function, and then goes all the way to 4, but does not include 4. So the domain would be the interval from negative infinity to 4, but we do not include 4. Okay? And the range, the largest y value I have is positive 4, and then, we include all these other y values, but this function here shows that the graph goes down to negative infinity, so we go to negative infinity all the way up to positive 4. And so that's our range. Okay? Now, the other thing is showing a point discontinuity, all right? And the question is, on this one, well, what's g of 2? Okay, what's the y value when I plug in 2? Now here's what I notice here, is that we have this line here, negative 0.5x plus 2, okay? This exists between when x is less than 2. So I'm going to have this function when x is less than 2, okay? But we don't include x equals 2 on that function, okay? The next one, quantity x minus 2 squared plus 1, exists when x is greater than 2, okay? Do we include 2 anywhere?
No, so that's why it's an open.
That's why there's a hole, okay? So because we don't include 2, there's no value for that, and g of 2 would be undefined, okay? Okay, the next one, which graph represents the function? Okay, on this one, so we've got at negative x minus 2, so a negative slope here, and we include x is less than or equal to negative 2. So we have to include that negative 2. So because this has a hole at negative 2, that doesn't work. No. No.
No.
Okay. This one includes 2, but this graph here is what? Non-linear. It's not a line. Okay, this graph up here, negative x minus 2, this is a linear function.
Yeah.
So if this is curved, it doesn't work. Okay. Then you change negative x squared between negative 2 and 0. We don't include either of these. Okay. And then we have the line just y equals x beyond when x is positive. Okay, so it's just going in a positive slope that direction when x is less than 0. Notice how we don't include 0. So there's a hole at 0. So this is our graph right here. Okay. Okay, given the graph here, and this is the last question, given the graph of the function f of x, what is the value of negative 2? What do you guys think? What's f of negative 2?
It would be
0. Yeah, because there's a point there. There's a hole down here on this graph. So we have to look, where do we have a point? So the value would be 0. Okay? The domain of this function, okay, we go from, it's going to go up to the left to infinity, so x goes to negative infinity. Okay, we stop here at 0, but then we jump back down here, and we include negative 2, but then here we pick that graph back up, we change to a positive, another parabola that goes all the way on. So our domain goes from negative infinity to positive infinity. Okay. Hope you enjoyed this video. I know it's kind of a lot of stuff, but it's all good stuff. See ya.